Hello, everyone, and welcome to our webinar, The Journey to a Digital-Centric Chemicals and Materials R&D Lab. Today's event will be recorded and made available to all attendees afterwards. I'm the host and moderator, Chris Farrow. I lead NThought's Material Science Solutions Group. In my 10 years at NThought, I've been a scientific software developer, technical trainer. I've held various leadership roles within materials and other domain areas. Prior to NThought, my academic career was focused on techniques for studying structure-function relationships in materials. I'm joined today by our speaker, Mike Hyber. Before introducing him, I'll present some introductory material, and then Mike will take it from there. We'll end the session by answering as many of your questions as we can get to. Feel free to submit your questions at any time during the webinar. You can do this via the question module on the GoToWebinar panel. So first, a little bit about NThought. We've been around for about 20 years, providing solutions for science-based businesses. Our focus is applied digital innovation, which is about leveraging technology to create better processes and workflows for science-based companies. We have offices all over the world. Mike and I are in Austin, Texas, which is our headquarters. We have additional offices in Houston, Cambridge, UK, Zurich, Switzerland, and Tokyo, Japan. And at NThought, we're seeing a lot of the changes that are coming to the chemicals and materials industry. This is, some of these changes are summarized quite well by Lux Research. So here's some quotes from there. To go over that, digital transformation is expected to touch large segments in the chemicals materials industries in the next decade and the one after. What we're seeing is that companies are looking for new business models that they can help them maintain or grow their share of a market that's becoming more diverse and more specialized. They're looking at digital tools that can help them provide additional services for their customers or get them more involved with how the customers produce value. For example, people are looking for ways where technology can help a material buyer optimize a material before purchasing it, thereby giving a higher level of service and creating lifelong relationships. There's various ways, in fact, that we're seeing chemicals adopt many digital transformation technologies or digital technologies to this end. We're seeing people adopt data management systems and electronic lab notebooks, analytics platforms. A lot of companies are engaging in materials informatics. They're doing data-driven experimental design. They're doing AI-assisted materials discovery and development. In terms of education and staff augmentation, they're building science and materials informatics teams. They're training scientists to have digital skills so they can solve some of their own problems on the ground in the lab. They're educating staff more generally, just so they become more aware of what can be done with digital technologies. And we're also seeing widespread adoption of agile principles and organizational structures to help foster cross-disciplinary collaboration and innovative thinking. We'll be touching on some of these topics in the webinar. When it comes to digital transformation, it's important, just as important how you do things as it is what you do. I mentioned earlier, the North Star for transformation that companies are looking for is those deeper relationships with clients and new business models. Digitization and digitalization, which covers a lot of what was on the previous slide, those are means to that end, but alone they may not get you there. Companies who are looking for new ways of doing business must consider how their value generating processes play into that, and they must consider perhaps new processes that don't inherit the limitations of the existing ones. As Mike is going to show you, we advocate for a process or an approach that can grow beyond digitization and digitalization and provide the scaffolding for real business, digital business transformation. Of course, this all has to be done while keeping the business running, and that's what this webinar is about. We'll be providing you with a rough map that's intended to guide you towards transformation. Our approach to this, NThought's approach, comes from our scientific expertise, which we combine with software innovation and organizational change and education to transform companies. In the Material Science Solutions Group, to which Mike and I belong, we are driven to transform R&D laboratories, which have been largely underserved by digital transformation trends. Throwing buzzwords aside, like digital transformation, science and technology have always advanced hand in hand, and our passion is to help materials and chemicals companies keep pace with the rapidly changing technology landscape to better compete now and in the future, that is. So with that, I'd like to introduce my colleague, Mike Hyber. He's an application engineer here at NThought. His entire career has been dedicated to problems like this. He has his educational experience spans material science, engineering, polymer science. He's had multiple postdoc positions studying, among other things, organic semiconductor materials and devices. His passions overlap heavily with what's in this webinar: laboratory automation systems, automated data analysis, machine learning, data science for materials, physics-based simulation. Honestly, if I say more, I'll have presented the entire webinar. So what I'll do right now is hand it over to Mike. Thank you.
All right, yeah, it's a pleasure to be here. Thank you for everyone for attending, signing up. I see some faces that I know, either personally or from my LinkedIn network, so thank you for coming. As Chris mentioned, I have a lot of experience dabbling in these areas in my academic career prior to coming to Enthought, and I've only sort of built on that, working with collaborators and colleagues here at Enthought. It's an area that I'm very passionate about. So yeah, I'm going to talk through this topic here called building a digital-centric lab, and I'll explain what that means. So this stems out of an effort that Chris and I worked on for a while now, as we look back over our experience in this industry, our experience talking with people working in this space. In last December, we published a white paper, which was distilling much of our experience and thoughts about working with industrial R&D labs over many years into a framework to help our researchers, lab managers, et cetera, develop sort of an understanding about where to start, what to shoot for, and how to find success along the way throughout their R&D digital transformation process. So if you want to read more about this, you can find the white paper by following this link here. But I'm going to go into a lot of content that's in the white paper in this talk today. So in the white paper, we presented 5 stages that a lab may go through to become eventually a digital-centric lab that can operate orders of magnitude faster than what was possible a few decades ago. So 5 stages are, most labs that we see start out at stage 1, which we call the human-centric lab. This is sort of the traditional way of doing science and R&D product development. And then as we start adopting different types of digital tools, we see a progression along this axis here, where stage 2, you become a data-informed lab. In stage 3, you become a data-driven lab. And then with that foundation, you start to reach stage 4, where you're able to now become a transforming lab and start doing things very differently than what you have been doing. And before ultimately reaching sort of the end point on this line here, which is stage 5. The goal of a digital-centric autonomous laboratory. Now I'm going to dive into each of these 5 stages further today. I'm giving examples of what can and should be happening at each stage and how to find progress. Every lab potentially is starting at a different point along this path. You may already even be dabbling with bits of things that I'm going to talk about. Even if you maybe see yourself as stage 1, you may already be dabbling with digital tools that you'll see in stage 3. Or stage 2, 3, and 4. But this provides a framework for moving yourself as a lab, as an organization, towards new capabilities and that enable new business models. And so what do we see industrial R&D labs doing? As we see labs planning out their future and preparing for this, we see distinct categories of a strategic choice that are being made. Some labs are actually ignoring this digital wave, and they're kind of clinging to their old ways of working, either due to fear and uncertainty about what to do, or the feeling that maybe this is just a fad that's going to go away. And they're hoping that they'll still be successful in the future. But many labs increasingly are realizing that there are new capabilities. This isn't a fad. This is a real trend, and it's real for a reason. It's because it creates a more valuable, better business. And so they're committed to doing something. So what is that thing that they want to do? Well, some labs, they want to be innovative and they want to adopt new digital tools, and they see these tools out there with the promise of what they can do. And they take very technology-driven approaches towards implementing change. And we often see that these approaches for doing it are highly likely to cause resistance within the labs, within the organization, and ultimately failure. And we can see this beyond materials and chemical R&D. Digital transformation is happening across the economy in many business segments. And there are numerous examples of big failures that companies have tried big digital transformation things, and they failed because, again, they've taken very technology-centric, technology-driven approaches towards their business transformation. And what we're seeing in many industries and also in materials and chemistry is that the most successful labs and companies realize that culture change, process change are the most critical and challenging parts of digital transformation. And they tackle these problems head on as part of their digital strategy. And that's the approach that we recommend people to take. So what are the common problems? I'll explain this a little further. What are the common problems with the technology-driven approach? One of the big things you see is that research staff end up resisting the new technology tools that you're trying to implement, and that the effort to introduce new technology tools ends up actually reducing productivity instead of increasing it, which is the whole reason why you underwent this digital initiative in the first place. And so why does that happen? Well, oftentimes the technology tools chosen, for example, by IT professionals, by laboratory R&D managers, they don't understand all of the details of what happens in the lab day to day, and so they try to choose tools that are flexible and cover a lot of use cases. But oftentimes you'll find that these tools are not flexible enough to meet the varied needs across multiple labs and business units. And so, and despite what an enterprise software vendor may tell you, creating highly flexible software tools that can be customized is really hard to do. But it's really important to enable research, because research is very dynamic. You need that flexibility in order to meet the needs. And so a one-size-fits-all problem solution is almost guaranteed to leave some people behind. And so you need to be cognizant of that as you're planning out your digital strategy. The second point here, if you're mandated to adopt a new technology tool, maybe it's a new data system or a new software tool, researchers will then, with this sort of non-ideal forcing of a new tool, researchers will conform their processes to that non-optimal technology and move away from what they found to work best in their lab. And in extreme cases, researchers will even develop parallel systems where they'll comply with the requirements of the company, of the management, but then they'll keep their own separate systems on the side and try to run both of them simultaneously. And this leads to non-idealities and inefficiencies in the lab. Now, I've heard stories of lab staff being forced to comply with corporate data archival mandates, for example, and they're forced to use very generic data interfaces. And this results in significant decreases in knowledge generation rate, and it can ultimately lead to expert staff retention problems. The third thing is that technology tools chosen, while even if they work fairly well for your problems, as a whole, they may not actually solve the most important problems that's limiting innovation in your laboratory. And so in some cases, they don't actually tackle the limiting bottlenecks that you have in your lab, and therefore these tools are underutilized and have minimal impact on innovation in your lab. And so it's critical not to take a hammer and go looking for nails when you're undergoing digital initiatives in your lab and in your company. And so the question then is why is a culture-driven, problem-driven approach that we recommend usually the best strategy? The first one is to overcome this resistance is that research staff are engaged from the beginning and truly own their new digital tools that they use in the lab day to day. And they own the data products that they produce. They feel ownership over that data, and they feel proud of the things that they're generating and how it connects to growth of the business. And so while focusing on engaging these primary users is as a critical part of any change management strategy, here it's more than that, right? Research staff need not to just be simply users of their digital tools. They need to be equipped with the skills and mandate to drive evolution and continued digital innovation. So they research as you do things, as you develop and you learn, the tools need to learn with you and they need to evolve. And so we need to place researchers in the driver's seat of this process of digital transformation. Secondly, as we're seeing, agile development allows researchers to discover throughout the process what data really matters, how to best gather that data and how to organize it for secondary use. Becoming a digital-centric lab in a business is challenging and complex. It's a complex problem with a large number of unknowns when you're starting out on this journey. And an agile approach allows your teams to experiment and learn quickly from inevitable failures and find out what works best in their lab to continue moving forward and not spending a lot of time and money on something that has a high risk of failure. It's about iterating and learning and building that into your process. The third one, with this problem-driven approach, continued investments in digital can be justified by successes that yield quantifiable value in 1 to 2 year time frame, instead of waiting for 5 to 10 years for these kind of initiatives to bear fruit. In a large process-driven business, a successful transformation will require sustained investment, on the 5 to 10 year time scale. But most companies need to see tangible benefits along the way in order to justify that continued investment. You simply can't wait till 5, 10 years later to see this impact on the business. And so a problem-driven approach where you're solving critical problems that you have now and showing results is really critical for building momentum around digital transformation. So to illustrate these stages and provide some more concrete examples, I want to walk you through a hypothetical lab in an electronic materials business, which is an area that we at mThought have worked in frequently. That's an area that I've worked on personally even before coming to mThought. So it's a nice example story that we can tell to sort of give you a picture for what this might look like, in a complex materials business. So in this electronic materials business I'm showing here, you have a company that produces a wide variety of highly specialized polymer formulations that are customized and sold to electronics manufacturers. And these materials are critical components that form that power our modern day life, right? The electronic visual displays that you find here, the semiconductor microchips that power our laptops, our cell phones, and all of the other things around the world that use that technology. And in these industry, formulations are typically deposited as thin films, and these films serve a variety of functions in whatever device it's going into. And these are complex, highly engineered materials where the product development scientists are tuning these materials to have very important critical properties such as printability, controlled electronic properties, controlled optical properties, good adhesion, good thermal stability, good shelf stability, etc. And so you can see here, only listing sort of even the categories of properties, you can see this becomes a very highly complex design problem where you're trying to optimize, maybe at least 10 different properties that ultimately represents a good material that the customer wants to buy. And most labs have been doing this for years, right? The semiconductor industry has been around for a long time, and there are products filling these market niches. And this has been done for many years using a traditional human-centric lab. And this is where most labs that we see start from. I mean, it's based on a way of doing research and product development over many decades. And it's worked. It's been the backbone for innovation for successful labs and successful specialty chemical companies for many years. And in this lab, expert scientists have learned how the numerous variables such as chemical structure, formulation recipe, processing variables affect the final materials properties. And so expert scientists have worked through academic training, through their work in the laboratory at the company, how this works and what are these relationships. And so when a new customer comes and says, I want a new material for my fabric, for my fab, it has properties X, Y, Z at a certain level, these experts can leverage their knowledge of process structure property relationships and reason about that and come up with a decent starting point for an experimental design. And this is how most labs have operated for decades. And it works, but it's slow. So what does this process look like as an example in an electronic materials lab? So here we have a lab where you start out at the beginning of this process, the very beginning where polymers are being synthesized in the synthetic lab by chemists. They're then being formulated by adding additives, solvent, etc., to create a formulation. These formulations are then passed off into and taken into a clean room for further processing, where the formulations are potentially spin coat into thin films, and then patterned using the photolithography process and ultimately characterized, for example, looking at imaging to characterize the resulting pattern. There are many other characterizations and things that happen, but this is just an example of sort of a high-level workflow. And this process, as we've seen with companies that we've worked with, can take many days, even an entire week to go through this whole thing. And so every week, as you're trying to meet a customer demand, there's limited amount of iterations you can go through to form a highly engineered material that your customer is going to accept. And so this is in the end, it's a slow and inefficient workflow. It works, but it requires a lot of manpower, a lot of time, and a lot of materials resources to make it work. Along that process, right, data is being generated, and so most of the labs we'll see have sort of what we call legacy scientific data generation and storage systems, where measurements are being done on instruments, potentially being transferred via USB drive over to their analysis workstation, or even cases where data is being recorded in paper notebooks still being carried over to their desk and then transcribed, into an Excel spreadsheet. These spreadsheets are then highly prized and valuable. These are the most important data reporting format most of the time. And usually then these will be put somewhere on a network shared drive for archival. And while these spreadsheets may be technically centralized and shared with other researchers, finding data of interest within them, within a sea of spreadsheets, sifting through other files in project directories is hard and it's slow. And this results in the reality that these files are actually very rarely referred back to for secondary analysis or for as information to help you design your next series of experiments for a new project that comes down the line a month, a year later. So to get beyond this, we need to move towards what we call stage 2, which is the data-informed lab. And so this is where labs get started with their digital transformation, and they start getting data organized. And this is a foundational step for any kind of digital transformation initiative. So the key benefits that you can expect out of a data-informed lab is that data is organized and available via a search interface for use in visualizations and analysis for improved decision-making. And the new data from routine measurements that you've been working on for a long time, this is automatically analyzed and saved in a database, thereby removing human bias and variability from that process. And with this in place, junior researchers can learn from previous work and they can become more productive, which frees up time of senior researchers to tackle more complex tasks in the lab. So what does this look like? If you're a lab getting started, maybe you don't have a good data management system, where do you start? What does this activity, this transition from stage 1 to stage 2 look like? Well, first you need to get your data organized, right? That was the first point. And so if you're getting started on this process, there's a lot of questions that you'll have. Which data should go into the database? If I have a lot of data, and I have maybe even a lot of historical data, it's going to take a while to do all of it, to centralize and organize all of that data. How do you prioritize then and evaluate different types of data that you're producing now or that you have in a giant swamp of shared drive? How do you prioritize that? And so, and then once you've done that, how should your data be organized so that it is useful and not just a data swamp somewhere that again is there, but nobody really wants to use it because it doesn't help them with their day-to-day work. And so what we often promote with our clients is to do what we call laboratory assessments. And these assessments are essentially a formal assessment of a typical process of what happens in your lab. And many labs, haven't done this, or it's been many years since they've sort of looked inward at what they do in the lab and sort of formally document the process. It's just sort of in the scientist's head. This is what we do, and as new junior scientists come, they learn from the experts what to do. But these formal assessments can really help you take stock of where you're at now and then prioritize what to do. And so in this case, I'm showing here an example of one very small portion of a process from one lab, this being a formulation lab where their polymer materials are being brought into that lab, and then the formulation chemists are adding, putting additives in there, performing various intermediate characterization, and then making a decision about whether this is a good formulation that I should hand off to take into the clean room for the subsequent parts of the process. And so by making this note in this documentation here, you can note what other processes we typically do, how long do they take, the data that's generated at each stage, where does that data go, what format it is in, and you can start documenting all of these things. And then where are the critical decision points along this way where I decide where to do what, where to go next. And so for moving to stage 2, it's really important to take a look at the data flow, right? Because the first step is to get data organized. And so when you look at this data, you can say, well, let's say we want to look at one of the spreadsheets. This is maybe an Excel template that our synthetic chemists use, and they fill this out when they make new candidate polymers for our formulation. And so they may have a spreadsheet that looks something like this, where they're noting down a variety of different important metrics, such as what monomers they are using and how much of it, what solvents are they using, what initiators, et cetera. These are all details that a synthetic polymer chemist will be very familiar with. And they know what's important here, and so they've been documenting these things. Maybe they're in paper notebooks, or maybe they've been transcribed into an Excel spreadsheet for digitizing that data. And then maybe they go on and they characterize the products that they're synthesizing. They're looking at, for example, the molecular weight of their polymers, looking at the distribution and some of the key features that come out of a molecular weight characterization. And then going on to also look at the chemical structure, looking at IR spectroscopy or NMR spectroscopy to identify the chemical signatures that indicate to them, did I make the type of polymer that I set out to make at the beginning of this? So this kind of data is, experiments are already being run in your lab. How do we figure out and pull out what's important and get that, make sure that those things get put into the database? To do this well, it's really important to engage these experts in what we call the data modeling step of this. So a data model is basically a structure that is a formatted structure for what data you want to store in your database. And it's important that experts be involved in this because they know what data matters. They know the important pieces of data to include and maybe some of the superfluous or extra stuff that's not that important. And if you want to, maybe we leave that out for a first iteration. And then how does this data model organize so that once it's in the database, I can actually find something interesting, find something that's useful to me when I go on to make decisions later in the lab or later when I'm starting a new project. And ultimately, the idea is to reach a state like this where you have continuous automated data ingestion. So as measurements are being performed on these laboratory computers, the raw data files, the spectra files, the images, whatever that may be, is being automatically ingested into the database. And you can have data analysis scripts that are being automatically run on these files as they're being generated and make this data then accessible to all the scientists in the lab that have access. So what does this look like once you have it in place? Right? You have centralized data, you now have an ability to access this data programmatically. And for example, you can use modern digital tools like Jupyter Notebooks and Python programming language to pull this data from that database, run searches and pull in and generate these sort of custom tables of data that get you started with answering the questions that you have. You can then take that data and you can plot it in interesting ways, and custom plotting that allows you to inspect your data in ways that go beyond what potentially the instrument vendor software comes with. And so you can have a more richer, deeper way of looking at your data and then making better decisions based on that. You also have the ability for doing statistical analysis using a wide variety of tools, and there are many others. The scientific Python ecosystem is full of really powerful, really readily accessible software tools for doing scientific data analysis, and there's tons of documentation for how to get started, and it's definitely accessible to any laboratory scientist. It's no longer true to say that I'm simply an experimentalist, this programming stuff, it's not for me. Every scientist in the lab can do this. And if you need examples of how this happens, we'd be happy to provide those to you to get you motivated and able to do some of these more advanced and ad hoc analysis that help you in the lab make better decisions. So then after that, once you have data organized, the idea is now what can we do with that beyond just sort of ad hoc scripting analysis? Well, we can start playing around with machine learning and artificial intelligence and inject this into our process. And so as our researchers are making decisions, these decisions can be informed by recommendations from AI and machine learning. So key benefits of a data-driven lab is that decisions are derived directly from the data, reducing human bias and errors in decision making. And the design objectives, like we have these complex multi-objective design problems that we're dealing with as material scientists, these can be reached in far fewer numbers of experimental iterations. And in addition, making good technical decisions becomes less reliant on the judgment of experienced senior researchers, people that are retiring, and the need to transfer this knowledge to a new wave of junior scientists. And having these tools in place allows them to feel comfortable making these decisions quicker because they're informed by data. So what are the big problems? For any of you that are out there that are following sort of the promise of machine learning and AI for materials and chemistry, you'll find these examples of big revolutionary things that should happen, where these tools allow very accurate predictions that help solve big problems in materials discovery and development. So what are some of these big problems? So for example, the first one, it'd be great to have a machine learning AI algorithm which could tell you which parameter combinations will produce a formulation with desired properties, right? That's basically the whole design problem. If it could just tell me what to make in the lab, that would be great. That would be transformative, truly. But then there's also the more advanced things like, okay, of that, a subset, which of these fall within our current intellectual property portfolio or are patentable? And then furthermore, which of these can be cost effectively manufactured at scale? Right? These are obviously highly valuable problems that if a digital tool could help us with these problems, that would be great. But some people think that machine learning and AI are some magic thing that's just going to solve all of these problems. And that's sort of that's a misguided view of, and it's a overestimated realization of what these technologies can do today. And one of the main reasons for that is that solving these big problems will require a lot of really high quality data to do it. And however, most labs don't have a lot of data. It's the most common challenge that we see when we encounter this with our clients wishing to leverage machine learning is that they don't have a lot of data. They have some data. They have data of potentially varying quality, but they simply don't have the large numbers of data. They don't have big data. And so the source of this is what we call the curse of dimensionality. If you were to look at this input vector here of all the different parameters that control the output material properties. When I first showed this, so we showed maybe 5 to 10 little boxes here. In reality, these are representative. There's actually many, many more variables. If you're looking at the entire chemical space of what you could potentially synthesize, all the different additives you could add in the ratios and how you would process that material. You're looking at thousands of dimensions of things that are really important to the ultimate materials properties. And so if you want to be able to develop a predictive model that can understand all of that and make accurate predictions, you need a lot of data. And so a general rule of thumb in the machine learning community is you'll need 10 to 100 times as many data points or observations as you have number of features or dimensions in this example. So this means if you have on the order of thousands of important things that dictate your performance, you need tens of thousands, hundreds of thousands, and maybe even more data in order to make these predictions, these big predictions very accurately. And so this is very hard to do. So what does that mean? Does that mean machine learning and AI are no good? We should ignore it? No, it just means we need to define smaller, more tractable problems that are able to be tackled today and do have a meaningful impact on our ability to innovate in the lab. And so deciding where to start again can be assisted by these laboratory assessments that I mentioned before. Whereas in this case, we want to really focus in on these decision points that we're making in the lab. How can we use machine learning and AI to help us with any of the decisions that we make in the lab? It doesn't have to be the big decision. It could be something small, but we can leverage the data that we're generating and start tackling some of these smaller intermediate decision points in our workflow. And I'm going to give an example of this. So I showed you this workflow a little while ago showing the whole process at a sort of mid-level from polymer synthesis all the way through to pattern characterization. And in this example, I'm calling out one fairly small step in here, which is the spin coating step. Spin coating is a very easy process. If you haven't done it, I've done it many times in my academic research. You take a fluid, you put it on a spinning disk, it spreads out, and the solvent dries, and you form a thin film. It's not hard to do, but as you go in and look and you analyze your process, you realize you're wasting a lot of material when you do that process. And so this is a fairly straightforward problem, but it's a real problem that likely many labs face this problem, and they just haven't thought to tackle it in this way yet. So here's an example problem, right? The challenge. We currently coat an average of 5 films to find the target thickness every time we make a new candidate formulation, which consumes half of our formulation batch and limits our ability to perform other characterization downline. So if you've ever seen a spin coating measurement or experiment performed, if you were to bring your synthetic colleagues and watch it, as half of that fluid or more, up to 90% of the fluid spins off that film and is caught by the bowl. And all that hard work that they did performing custom synthesis for you is wasted. You will realize how valuable it is to minimize the number of wasted spin coating experiments. So our goal here then is let's reduce this waste. Let's reduce the number of spin coating experiments needed to reach our target thickness down to only 2. That's a benchmark we'll set for this task. But how do we convert that into something that machine learning can help us with? Well, we need to convert this into a prediction problem. So the prediction task is this. Let's predict the spin speed that I should use to achieve the desired film thickness given knowledge of the formulation recipe, right? The formulation chemists are going to tell us what's in there. and we're going to have some intermediate characterization results that they've already performed on that formulation. So all of that knowledge, whatever state of knowledge we have about that specific formulation, and all of the knowledge we have in our historical database about every other formulation we've ever made in our lab, can allow us to make a better decision about what experiment to do first. And you can do this using, again, Jupyter Notebooks, scientific Python ecosystem. I'm showing here an example using the very popular machine learning toolkit called scikit-learn. And I've developed this very simple machine learning pipeline, which takes in data, transforms it, and generates a predictive model that can, again, predict thickness given all of this information that I already have. And with this machine learning model, you can start to envision what would a decision support tool look like in the lab. So what do I want to see? If I'm the scientist in the lab and I say, okay, I have this new formulation, what do I do next, right? Well, ideally, we want it to tell me, again, what spin speed to use. And so you can imagine displaying to the scientific lab researcher this information here saying, in the dark blue line, this is my predicted spin speed curve. So this is how thickness changes and decreases as I increase the spin speed of the spin coder. And this dark blue line shows me the most likely outcome based on all the data that we've ever seen. This is being produced by our machine learning model. And the artificial intelligence algorithm is analyzing that fit and spitting back to you a recommendation. So it's saying, if I want to reach a target thickness of 2 microns, this is the spin speed that you should use in the lab. So you can prototype this sort of decision support tool. And this can be done, again, in a notebook. You can do this maybe in a couple of weeks and figure out, is this a powerful tool? Does it perform well enough that we want to then implement this in the lab? And once you've made that decision that this is valuable for us, you can go forward and then take that to the next step, where you can build an actual application that can be deployed in the lab. In this case, I'm showing a very rudimentary example of a graphical user interface desktop application that I've built for this demo purpose. This could be in a web interface. You can be whatever you want, but we can translate ideas, quick ideas that scientists have through prototyping in notebooks into end user tools that scientists can use in the lab to make, again, better decisions in search of more efficient laboratory performance and accelerated innovation. So once you have that underway, you're starting to dabble with machine learning and AI, you're starting to inject these decision support tools in your lab. You're going to start wanting to think about, okay, how do I start moving forward and moving towards tackling some of these big problems I highlighted? And this is a place where you need to start transforming and looking and exploring new ways of working in the lab. The key benefits of a transforming lab is that at the beginning, the generation of the most valuable data is accelerated significantly. And so this is data you already know is valuable, and you know you want to do it almost every time. Let's get that figured out. Let's accelerate that part of the process. And so you almost don't have to think about that. It's happening. Then this allows you to start exploring new data sources. Where can I bring in new types of computational calculations, new types of experiments that will improve our screening abilities and generate new, more informative data sets that improve our prediction capabilities? And finally, with a transforming lab, experienced senior researchers can sort of shift their focus to the bigger picture, looking at process improvement instead of the execution of daily tasks in the lab. It's a shift in focus. So again, how do you decide where to do this? Well, again, laboratory assessments can help, and they can help you hone in on these process steps. So for that first point, what are my bottlenecks? What processes am I doing that are really slow, that are just limiting my ability to generate 10 times more data than I'm doing currently with the same amount of people in the lab? So let's take a look at this workflow, and you can sort of, from that assessment, you can look at this workflow and start thinking about, well, how could robotic laboratory automation help accelerate this traditional process? And you can start scoping this out, or you can envision here with cartoons how you might group some of these tasks into certain modules and have automation along the way. But designing and automating the system is complex, right? This is a complex, difficult process. The idea you're going to automate this from front to end all at once is hard. It's risky. It'd be very expensive to undertake this all at once. And so as you're transforming and starting to dabble in laboratory automation, it's important to take this in chunks. And so I'm going to show you an example where we've done this with one of our clients, looking at this final problem, which is the film pattern characterization part of the process. So in this example, our clients were wanting to, again, measure their patterns faster, they're generating silicon wafers with a certain test pattern. And in the human-centric way of doing this, this required manual image analysis. The scientist would place a wafer on an optical microscope, take some images, do some annotations in the image analysis software that comes with the instrument, and then record this data down. And the problem is that they found that the evaluation results were highly variable between different researchers, which was leading to inconclusive results and lost time in the lab. So our solution to this problem was to develop, a low-cost automated optical microscope that would allow them to put their wafer, automatically have that system scan across the wafer and take images of the regions of interest, and present to the user an interface that allowed them to develop their own custom pattern metrology algorithms so that they could find things. For example, in this image I'm showing here, showing these lines, they could decide, what about these line patterns do I care about as an expert? I'm maybe going to characterize maybe the spacing, the line width, roughness, other features. The scientists know what's really important, and we want to give them control over what's being extracted and teaching them basic image analysis algorithms so that they can take ownership over that part of the analysis. And as a result of this example problem that we performed with one client, we found a 40 times speed increase of this process to help them get ready for further automation of their laboratory in the future. And in addition to that speed up, because this is being performed in an automated fashion, both the measurements and the analysis, this greatly improved the measurement consistency so that they could feel confident in making decisions based on the data being generated. An additional place is to start looking for new sources of data. For example, many labs have computational groups, but oftentimes these groups are maybe disconnected or disjointed. How do we bring computational data into this where these are acting as new features for our predictive models? So even before we get started in the lab, what are some common series of computational methods we could apply to provide us with information and knowledge that helps us make more accurate predictions about what to do when it comes time to make things experimentally? And there's a lot of activity in this area doing what we call virtual screening, where you set up a series of different computational methods which generate increasingly informative data, but also are increasingly costly from the computational standpoint. But we design this in a way that we're learning as we go, and that the calculated properties don't always need to be super accurate. They just need to be informative and correlated to real properties. And you can design experimental screening methods in a very similar fashion. So that brings us to stage 5, right? You start reaching a point where now you can start removing the human from this loop here. You can see there's no longer an expert scientist in this loop. You may not do this everywhere, but in some certain places where things are starting to be well understood, you can start removing the human from the loop and allowing these algorithms to take more control as you start to feel more confident in their ability to make good decisions. So a key benefit of this digital-centric autonomous lab, where you can do it, is that computational and experimental data happens autonomously, 24/7. And with this data, optimal decision-making algorithms can be implemented to orchestrate efficient use of expensive human lab equipment and computational resources. And with this in place, experienced researchers, having gone through this 5-stage transformation process, have really understood what it means to transform a lab. They become digital leaders in your organization. They can go out and help other labs undergo this transformation. And they can start exploring new ways of engaging with customers that are much closer and using this data and using these unique capabilities to offer unique value. So what are some examples that we've seen like this? One really cool example that you can find that we've looked up from our market research is a company called Evonik, which is doing some really cool things in the coatings and formulation space. They've developed highly automated systems with artificial intelligence software wrapped on top of it that helps them interact with their customers in new ways. Evonik is one of them. There are other clients, especially in the paints and coatings industry, including BASF and Altana, and they all have publicly published information about what they're doing in this space. And these systems can produce a lot of data very quickly. However, these systems are also very expensive, tens of millions of dollars to develop this kind of system. And they're highly engineered for a particular workflow, which is fairly standardized in the coatings industry. And because that industry has a wide variety of well-established industry standards, they've made a long-term investment to buy and develop these systems. But there are other labs where things are much less standardized, or their companies are smaller, and designing a large complex system like this upfront carries a very high financial risk. And in these cases, an iterative agile development process that we've talked about here is much more appropriate to mitigate risk and allow you to show development over time and have a faster return on investment throughout the process. An alternative example of another lab doing really cool things is a company called Zymergen, which is an upstart company that recently went public. And with major investor backing, they've built digital-centric labs from the ground up. And as a startup company, they've been able to quickly go down this digital route. And they've been able to largely avoid the organizational and cultural change challenges that are faced by large incumbent companies in the industry. And you can see here they've prioritized and approached things a little bit differently than we saw in the Evonik example and in other players in the coatings industry, where they've placed a premium on flexibility and modularity here. They want things that are reconfigurable. It's a different way of designing automation systems that enables them to do some really interesting things and be more dynamic in their product development. And this is a very inspiring example, but most labs and companies out there are not starting in a green field, right? They need to transform labs that already support large existing businesses while serving their existing customers throughout the process. And so this is challenging. There are unique challenges to transforming a large existing lab, and you need approaches like I've illustrated here today to make that a reality. So with my final thoughts, again, as I wanted to re-echo what Chris said at the beginning, premium chemical companies are going to be integrating new digital tools with traditional specialty chemical services and become deeply involved in product development with their customers. This is the business driving force for this. And in order to enact this change, an important point is that digital transformation is the integration of digital technology into all areas of your business, from your sales and marketing to your operations and to your R&D. And this needs to fundamentally change how you operate and deliver value to your customers. And to make that happen, it's not just a technology change, it's a cultural change that requires organizations to continually challenge the status quo of what they're doing today. So with that in mind, if you have further questions about what we do in this space, you want to talk to us about what we do, please reach out to Chris or myself. We'd be happy to provide more examples and talk more about what we do, but I hope you found something in this talk that resonates with you, that's interesting, and we're happy to field any questions that you have at this time.
Hey, thank you, Mike. Very much enjoy seeing you talk about this. As Mike said, we're open to questions now. I've got one coming in. All right, this one, well, maybe Mike, I'll start with this. I'll get my webcam on here. I'll start with this one, then maybe you can jump in as well.
Sure.
And that is, how do you convince a group or a boss to invest in digital transformation? I'll take a first cut, I guess, and it goes back to Mike's presentation. Whether or not your group is thinking about an investment in things like this, you should have an intense focus on the business and what are the real needs. Part of that process of the laboratory assessment and a wider process or a wider investigation that ties the business down to how the laboratory generates value. You should be doing that on occasion. It's great when everybody in the laboratory understands how their work generates value for the business. Once you have that and you have that understanding, and sometimes you'd be surprised how difficult it is sometimes to get everybody in the room understanding things in the same way about how the business actually generates value or how the lab does. But once you have that, it becomes much, much easier to be focusing on where you're going to invest, not only for new initiatives, but just your energy in general. You can take an argument like, well, this step is inefficient, or this step is inconsistent. And then you can tie that through to, okay, well, if it's inefficient, it gets us, if we fix this, it gets us this much closer to being able to study or do one new contest a year where we're creating a specialty chemical with a potential buyer, or it gets us this much more time to make a material more robust because we don't understand our buyer's process Therefore, we have to make sure that this is suitable for a large range of processing variables. So the short answer is, understand how the lab contributes to the business, and understand the knobs that you can turn when it comes to efficiency and how the lab operates, the processes, and how turning those knobs affects the business. And that makes it a lot easier to start talking about investment, or to prioritize the time that people already have to be thinking above the level of the tasks, but at the process itself and how to improve that. So that's my take on that. Mike, you want to add anything?
I guess maybe I'll provide a little context, from the lab side. If you're a lab scientist out there, you don't even have to necessarily be a digital scientist, whatever that would be, to realize the value here. And if you're thinking, especially if you're a young or mid-career scientist, and you're looking forward, what's your career going to look like as a scientist as you move forward in time? Invest in your own skills. Invest in looking at these case studies. Find these stories, and once you start to see the potential, find these stories about how things happen. We try to do that as much as possible. Give concrete examples for what to do. But find these stories and think about how they apply to your problems in your lab. And then when you go to your lab manager or your business leader and you say, we should be trying this, you're not just saying, oh, we want machine learning, it's awesome. Like, no, you have very specific, like, hey, I see this part of our lab, like, it should be tractable. Here are some ideas I have, where can I get the skills I need to do that? Where can we get outside help to help us move in that direction? Take ownership over this, because this isn't going away, and this is going to be a critical part of every scientist's job in the next 10 years. I'm pretty certain of it. And so it requires pushing, right? You need to be driven. And so you don't need to know everything up front. It's a learning process, but everybody's learning, and that's part of the fun. That's why we became, scientists, researchers to begin with.
Yeah, that's a good segue to the next question, actually, about learning. What's the biggest lessons learned in transforming into a digital-centric innovation group that may not have been expected? I guess this could be answered in multiple ways. I'll talk maybe first about things that we've seen. I guess it was expected, but maybe not from the people we've worked with. We're finding that every company has people who are just naturals at this, and due to some reason or another, because they're earlier in their career, or because of the organizational structure has somewhat rigid rules about how people advance and the timing. You've got hidden gems who aren't able to flex this muscle that can really be leveraged in the lab to improve the processes. That has been a great thing to see happen, and it's been a big surprise to some of our clients, and they've had to rethink, oh wow, maybe we need to capture this sort of potential in one way or another. We've seen in one case an MI group get created to make sure that people like this are given some say in how transformation takes place. Other surprises for us is just, honestly, we take for granted, we're a technology company, we take for granted the technology and making it accessible. There's deep problems there that we've been dealing with for many years, but the barriers of bringing these ideas in can be very, very large. We've encountered severe barriers, for example, in IT, where there's an old idea, well, maybe not old, it's a valid idea that security is the top concern. You don't want your IP, you don't want secrets getting outside the company. However, I've been surprised with how stifling that can be for innovation. We've seen a place where people were trying to learn technologies, but they couldn't go to one of the top websites on the web to ask questions about how to code and how to do things, because security locked it down out of an overabundance of caution. And what it took to actually overcome that, even though there was alignment towards digital transformation up and down the organizational structure within this company, that was quite surprising, the effort that it took. And I think in both cases, it comes down to mindset change. It takes time to change people's mindsets. And it takes a lot of examples of how it actually affects them and their lives and their business. Those things have been surprising. Mike, do you want to add anything to that at all?
Yeah,
Any anecdotes?
I like the first one you talked about. I mean, that being, the company and the managers were surprised, and we were surprised at how awesome some of the trainees become. But even the trainees themselves are surprised at how easy it is to get started and do it. I mean, it requires work, of course, but they come through and they say, wow, like these are new capabilities that I have now. I thought it was way harder. Like I had it blocked off in my mind, especially when you're working with experimental scientists in the lab who at some point in their career decided, like, I'm not a theoretician, I'm not a computational person. That's not for me. And they sort of wall it off in their mind, whether this maybe happened sometime early in their academic education. And when they break down that barrier and realize it's accessible, and actually it has a big help on the work that they're doing, on their experimental work. Like they can still be focused on the work as an experimental scientist, but the ability to bring in these tools and help them in new ways, they are surprised. Like, wow, like I'm so glad that I bit the bullet and tackled this and put my effort into it.
Yep. So a couple other questions. I'll try to get to a couple of these and then we'll have to close because we'll be at time. But do we enable clients to use more advanced AI and ML technologies to solve difficult problems, for example, new solutions to deal with limited data? Yes, we can participate in that. We're actually in the midst of that right now with a particular client, and it is one of those hard problems. What do you do when you don't have enough data? The strategies that are being developed by the MI community are still maturing in many ways, but we stay abreast of that and are willing to work with people to help explore those things. So we are at time. Thank you so much for coming and listening to this. We're happy to answer any other questions you have. You can contact us, as Mike said, through these channels. You can also just get to us on our website and reach out. We'll be happy to have a conversation about things you found in the webinar, additional questions you may have. So thank you very much.
Thanks, everybody.